Okay, so we're just going to be doing another example of solving a separable equation. We're going to go ahead and look at a kind of application problem. We're going to pull it from section 2.7.4, and we're going to be looking at Newton's law of cooling. Which is given by dt is equal to k times t minus tr, where r sort of indicates that this is the temperature like of a room. And this is a word problem. So when a cake is removed from the oven, its temperature is 300 degrees Fahrenheit. After 3 minutes, in a room at T equals 70 degrees Fahrenheit, so the room temperature is 70 degrees Fahrenheit, it reaches the temperature 200 degrees Fahrenheit. And so the word problem asks you how long until it reaches room temperature. But we're going to go ahead and just turn this into an initial value problem and practice solving it. So the initial value problem for this word problem is going to be dt is equal to k times t minus 70, where little t is going to be in minutes and big T is going to be in Fahrenheit. I don't actually know how to spell Fahrenheit. And our initial condition, we're going to say that T equals 0 is when we're removed from the oven, well, the cake. And we were told that it's at 300 degrees at that time. And we're interested in solving for T. And sort of along the way, we're going to need to find K. We'll take care of both those things as we move through the problem. So we're continuing this example. Well, let me write continued right there. And so we can see that this is a separable equation. It has a function of t right there, and then a function of little t right there. Just the constant, like I said, is sometimes possible. Oh no, wrong button. And I can no longer erase those lines, that's fine. So our first step is going to be to take our dt d little t equal to k times capital T minus 70, and then we're going to rearrange it to big T, big dt, over T minus 70 is equal to k times d little t. I've moved all the big T's to one side and all the not big T's to the other side. And I'm going to go ahead and integrate it. So the integral of d big T over big T minus 70 is the natural log of T minus 70. And the integral of K with respect to T is going to be K times little t. Now we have to remember to hold on to our constants of integration, but we remember that the constants on either side will combine. So I'm just going to go ahead and have one constant right there. I'm going to do the same thing as I did in our other practice problem to get rid of the natural log around the big T. So I'm going to have e to the natural log of t minus 70 is just going to give me t minus 70 is equal to e to the kt plus c, which is going to be just some constant times e to the kt. Well, okay, let me do that in 2 steps, and then I'm going to stop doing that in 2 steps from now on. So that's going to be equal to e to the kt times e to the c. You can always do that with sums inside exponents. So I'm just going to say that some constant times e to the kt. Or t is equal to 70 plus c1 e to the kt. Now, I'm going to go ahead and solve for my unknown constant c1 using my initial condition, because that's something I know how to do. So I'm going to say, okay, I need t of 0 equals 300. So right here, that means that I should have 300 is equal to 70 plus c1 e to the k times 0. And e to the k times 0 is e to the 0, which is 1. So that's just 70 plus c1. That means that c1 should be equal to 300 minus 70, so it's just equal to 230. So the solution is big T is equal to 70 plus 230 e to the kt. We're not quite done here, but that's solving a separable equation as we learned it so far. The last step to this particular problem is that we have this unknown constant k in here, and we'd like to get rid of it. So to get rid of k, we're just going to use the rest of the information from the word problem. So I'm going to go back to the problem so you see exactly what I'm saying. But this, after 3 minutes, the cake reaches 200 degrees Fahrenheit. That's information that we have not used yet, and we need to now. So the temperature at 3 should be equal to 200. But we have the solution from the last page was 70 plus 230 e to the kt is temperature. And we want t of 3 equals 200. So we should have 70 plus 230 e to the k times 3 is equal to 200. Or e to the 3k is equal to 200 minus 70 is going to be 130 divided by 230. So just 13 over 23. Take the natural log of both sides. We'll have 3k is equal to natural log of 13 over 23, or k is equal to 1/3 the natural log of 13 over 23. So the solution is big T of little t is equal to 230 e to the, that t, which I put in a calculator before, and it's about negative 0.19. So negative 0.19 times t plus 70. Oops. And then from that point, we've gone ahead and solved the whole differential equation. Sort of an interesting point. When we learned about equilibria, we said that for this type of equation, the equilibrium is room temperature. For us, that was 70. And it's a stable equilibrium, so you should head there. But you're never actually going to reach it. So if you look at the solution to temperature, if you plug in any value of T here, you're actually never going to be able to reach 70. You're always going to be a little bit away from it. And the way that this question was originally written, it was just like a little trick to get you thinking about that. But you can go ahead and just look at that temperature and the limit as T goes to infinity to reason through that on your own.